Let's talk generally now about this thing called a redox reaction. When redox reactions occur, there is always this kind of equilibrium symbol I have in the middle, and there will be the availability here in this chemical reaction, certain kinds of atoms on the left and the right-hand side. And one of those sets of atoms is always going to do one thing, and that's called lose electrons. And one of those sets of atoms is always going to do something called gain electrons. That's a fact for redox reactions. Some kind of atoms are going to lose them. Some kind of atoms are going to gain them. When it's all done, the number of electrons on the right-hand side and the number of electrons on the left-hand side have to be equal. So if I have 5 electrons go this way in an overall process, then 5 electrons have to go that way, because I have to maintain mass and charge neutrality here. So it's not just the number of atoms on the left and the right stays the same. The amount of charge on the left and the right stays the same. I can figure that out pretty easily. If I add up all the charge on A and B and it's -6, then I better have all the charge on the right-hand side add up to -6. But I know a reaction is undergoing a redox process if the number of electrons going one direction is balanced by the number going the other. So what are some examples of, one other thing. There is a name that we give to losing electrons and a name that we give to gaining electrons. The process of losing electrons is known as oxidation, and the process of gaining electrons is known as reduction. Generally speaking, the idea of gaining electrons and being reduced, it actually takes work because you're actually having to put electrons into something. On the other hand, the idea of losing electrons is associated with the expenditure of, with the energy release that occurs. So oftentimes, when we look at chemical processes like a combustion reaction, you're going to see an oxidation process happening to something like a carbon-containing compound as it moves to higher oxidation states. What are examples of this? Well, let's take something like ammonia making nitrate ion. This was an oxidation process in which my -3 charge on the nitrogen became a +5 charge on the nitrogen. So this was an 8-electron oxidation process. Let's look at some of the famous kinds of chemical reactions that I do in class as demonstrations. And we can see that this is in fact the case consistently across the board. So here's an example right here in which I look at pouring hydrogen peroxide in my ear to get rid of earwax. It's a redox reaction, and the reason I know it's a redox reaction is because if I write down all of the oxidation numbers, then here we see oxygen is -1, hydrogen is +1 because of that hierarchy rule I had, and over here oxygen is 0. So my oxygen going from -1 to 0 is going to be an oxidation. My hydrogen, and in this particular case, my oxygen going from a -1 to -2 is a reduction process. Down here, looking at transition metals, I have a rather substantial change in the oxidation that occurs as I move from purples to greens to browns to clear. And you'll notice that my permanganate, which has a +7 oxidation number, becomes MnO4 double minus, which has a +6. We calculated that oxidation number earlier. Becomes MnO2, which has a +4, which becomes +2. Notice as I move from +7 to +2, I am moving in the direction of reduction because I am adding electrons. Exploding hydrogen balloons we've talked about before. Hydrogen and oxygen are both 0, but water is +1 and -2. The hydrogen going to +1 makes it oxidized. The oxygen going to -2 makes it reduced. Here's a typical combustion reaction. Here's some sugar which is being burned. This is very common to produce CO2 and water. Notice what always ends up happening to my carbon. it goes from being a lower oxidation number to a higher oxidation number. So the carbon is being oxidized. At the same time, something has to be reduced, and that's my oxygen here that's going from 0 to -2. There are also the famous reactions in which I explode stuff when I throw it into water. I throw some metal ion, some metal, alkali metal, some sodium, some lithium metal into water, reacts with the water, explodes. Notice the sodium becomes +1, it's being oxidized. Notice that the oxygen was -2 here, and it stays at -2, but the hydrogen, which was +1, can go to 0, so it's being reduced. So these are examples right here of where I have oxidation and reduction occurring in each of these processes. I wouldn't know that these were different from solving salt and water or from an acid-base reaction unless I were to write down the oxidation numbers and then look to see whether or not there was in fact a change in the oxidation number for each of the atoms. But do know that as I see this happen, I always know that something is being oxidized because it is losing electrons, something is being reduced because it's gaining electrons. And as we'll see in just a moment, it turns out that the number of electrons going the one way and the number of electrons going the other way have to add up and be equal to each other.